Okay, now, the thing that we just want to do now, after the very basic and brief intuition that we got about what do we mean by multivariable regression analysis, let's jump into, I should say, our analysis right now here, and just start with the some basics of the multivariable regression analysis. I call that in a sense that we just work with some data. The data where I have just picked it up, you can find exactly the parallel, I should say, analysis as a non-Bayesian regression analysis that we have done in one of those lectures. And these data sets, they are essentially states data sets that we're just going to work. It's the state data sets, and you will see that we have lots of them. We are just going to go with the state X77. I'm just going to click on the promise, and you will see that the data is now stored as a state X77. We have, if you remember from the things that we have done before, this data set, which is state.x77, it consists of 50 states, which every state is in a row, and we have 8 covariates that we have. And also you can check the head of that data set as state.x77, and let's say check on the first 5, for example, row of this data sets. You see that from the Alabama, Alaska, Arizona, Arkansas, and California, we have, I should say, 8 predictors as a population, income, illiteracy, life expectancy, murder, and higher school education, and also the frost as a temperature and the area of those states. Then if you remember what we had done in that those lectures, when we talked about the non-Bayesian ones, we created, I should say, a data sets. We called that the states, and we said that, okay, we are just going to come with this state.x77 and just simply pick up some covariates. We said that I'm just going to pick up all those states. Then for, I should say, for the covariates, I'm just going to go ahead with the population. I'm going to also pick up, I should say, the income. Also, I'm just going to go ahead with the illiteracy. And the very last one, which depends on your study, you can just go ahead with the area then. And I'm just going to store that object into the states. And if you remember, we checked at the class of the states that we have created, and we noticed that's a kind of a matrix. However, we needed that object to be as a data frame. That's why we put that into another line of code, which is that as data frame. And you will see that the state, if we just run the class of those states, you will have the data frame ones. That's essentially, that's what we have talked about that. And we know that from our previous studies that essentially the regression model, the data that you're just going to call into your model is going to be as a format of the data sets. You cannot just create a matrix and just have it as an input from the data argument inside your, I should say, regression analysis then. And that is the reason I decided to convert the class of my data sets, which initially was as a kind of a matrix or array, into a data frame, simply by calling this line as data frame. Okay, and now we check the state, the class, and now the thing that we just want to do is that now we have everything ready, and we just want to, oh, by the way, the thing which I forgot to do that is that because we just wanted to make the model, I should say, based as a murder, I forgot to include the murder covariates as a response variable into my data sets. I'm executing the line, and it seems that everything is fine, and we can also check the head of the data sets which I have. With the first 3 lines, you see that now we have for 3 states, Alabama, Alaska, and Arizona, only these covariates which I selected from that data sets, which is murder, population, income level, literacy level, and the area in those states then. Okay, now, the other thing that we just want to do right now, it seems that all is ready now, and now we can just create our multivariable regression. Okay. In order to do that, you remember we have always talked about that we just go ahead with the RStan package in order to just do our regression analysis in R using the STAN, I should say, environment, which is going to be a dynamic Hamiltonian Monte Carlo. This is the function which I need to just run, I should say, my multivariable regression analysis, and I press the F1 in order to have the help menu opens, that it helps me what arguments do I need to just have as an input for my function. The first one is a formula. For the formula, I just want to model the murder as a function of the other variables, which I can say here it's going to be the population plus income plus illiteracy and plus area. This is going to be the line which represents the formula of my model. It says that the murder is going to be a function as the other covariates which I have: population, income, illiteracy, and the area in that model. You can notice that I do not have any nonlinear terms, and also I do not have any, I should say, interaction terms, that we are just going to talk about that a little bit later, how to include interaction terms and nonlinear terms in the model that we have. Okay, it was about the first argument. We are just going to go as a default with the Gaussian family in our model as a distribution, and now as one of the other arguments, I'm just going to go to choose the data, which I know the data is going to be a data frame which I created, and that's going to be the states which I previously converted that, I should say, as a data frame, the matrix which I had. Okay, and the other things which we can just include in this model is going to be, for example, the number of the chains that we just want to run the model, or the number of the iterations that we just want to have, or for example, the action that we just want to do with the the missing values, and which I should say we do not need to just go ahead with this. Also, at the same time, we just want to go ahead with the defaults that we have for the priors, which is going to be, I should say, the thing that is going to be the Gaussian, which the model is going to come. We talk about, for example, how to get the information from, I should say, of those priors in the lectures before. You can extend the knowledge that you got from there to take it from here, but at this stage, we are totally fine to just go with the default. And I should say, the algorithm that we are just going to go ahead with it, it's going to be, I should say, the sampling algorithm, which is essentially, that's what we have done so far. We sample and browse from the posterior distributions inside the parameter space of our model. We do not go ahead with the optimizing or mean field or full rank, which some of them, I should say, like the mean field and the full rank is going to be used for, I should say, for some variation of the Bayesian methods that we are not, it's beyond the scope of these tutorials there. But before I just execute this line, I'm just going to create a name. I say that model A, but I call it with the M, which it says that it's going to be the multivariate because we had model A before, and now it seems everything is ready, and now we are ready, I should say, to execute this line by pressing Control Enter, and the model, you see that it takes some time, and the model, it's fully processed, and it took, I should say, this fraction of time after the warm-up, and with the sampling that it converges to, I should say, with 1 point in our, I should say, parameter space, and now the model is done. And now in order to show that, I'm just going to go ahead with the summary. This is essentially you can just follow all the steps which you have done in the single variable regression analysis, but now here it has more variable, and everything that we have learned with single variable regression is going to be valid for the multivariable regression analysis. I'm just going to, as an object, I put model AM and execute the line, and we see that the model is, I should say, it's here. We have, very quickly, we are just going to describe what these stuff means. Then we just go ahead with some diagnostics of the model then. You will see that we have some model info when you run the summary of your multivariable regression analysis. The function that we used is stand generalized linear models. The family of the distribution that we used, it was Gaussian, and the formula that we adopted, it was this. And the algorithm, it was sampling. And I should say we took, 4,000 samples. For 4,000 samples that we just had to draw from these ones. And also we had 50 observation or 50 states, and we had 5 predictors, which they were, I should say, murder, population, income, illiteracy level, and the area of those states. We have estimates. You see that we have an intercepts, which we look for, I should say, for the mean values of them. Then if we just want to just write a regression model, we can say that, okay, we have an intercepts, which is going to be 4.1. And for example, you see that the income and the population, they have almost 0 intercept, but also we have for the illiteracy, we have this value, and for the sigma, which is essentially the hyperparameters in the Gaussian distribution, we have this value. And also we have some other diagnostic terms. We have, I should say, for example, the RAT, as long as you will see, as long as the RAT is 1 or less than 1.1, we can say that, okay, the model is good. It has converged into 1 point inside our parameter space, and now it's safe to just go ahead to just run further analysis of our data sets then. Then essentially what we had here, it was the summary of our multivariate regression analysis. However, in order to see what prior has been used for this model, we're going to use the function's prior summary, which is a function inside the R-stand arm. And I'm just going to go ahead to just run the model AM, execute the line, and we will see that what happens there. We have a section with the priors for the single variable regression analysis in the Bayesian frameworks, which we saw that essentially everything we see here is the same exactly there. Then you can, whatever you learn there, you can extend it from here. You see that for the intercepts, we used this prior distribution as a normal, which has been scaled. And we just saw how the scale can be done. We can compute the scales, which is essentially a ratio of standard deviation of your prime predictors with the standard ratio of your, I should say, the response value. With the coefficients, you see that with the coefficients, we have, for example, based as, I should say, the population, income, literacy area, we have the center of them. And I should say the standard deviation of them. And also for the auxiliary, which is the sigma of the standard, I should say, of the Gaussian distribution, you see that that's an exponential with the rate, and I should say it has been autoscaled by, I should say, by a ratio, and it took it to 0.27 as the rate of our exponential distribution. Then I recommend you then, in order to see how you can manipulate these, I should say, these priors, how you can introduce your own distribution based on the knowledge that you have, or also how to just, I should say, remove the autoscale and to just keep it a weakly prior distribution as a null distribution. You can go back to the section that we covered on the single variable regression analysis. At the part that we talked about the priors, you can just learn those stuff there and extend it here to the things that we learned over here then. Okay, on the next tutorials then we're just going to do some kind of diagnostics that we had done. We have been doing that before to continue with this multivariable regression analysis within the Bayesian framework.